Hey there, organickers. I want to do a quick video on oxidation state and how that's different from formal charge. You've already learned how to calculate formal charge, but we're going to start talking about oxidation reactions of alcohols and reduction reactions of carbonyl compounds. And in order for you to understand why those are oxidations and reductions, I need to show you how we calculate oxidation state. So oxidation state is really, the calculation of oxidation state is a different method of electron accounting that differs from formal charge. So I want to go ahead and show you how that's different, right? And why certain reactions are oxidations and reductions. So let's go ahead here and have a look at these two molecules, all right? So we have methane and we have CO2. So I'll expand them and I'm going to make this a little smaller. All right. So if you recall the calculation of formal charge, one easy way to do that is just to draw a circle around all the bonds, right? So you're splitting those bonding pairs in half, and you assign one electron from each bond to that particular atom. So for this carbon, that would be 4 electrons I'm assigning to carbon, right? And this is how we calculate the formal charge, right? So I take the group number, which is 4, minus the number of electrons that I assign to that carbon, which is 4, so that's going to be equal to 0. So my formal charge is 0. If I do the same thing here for CO2, right? And I'm going to assign 1/2 of each bonding pair to that carbon. So I start with the group number and subtract the number of electrons that I assign. So I'm going to assign 1 and 2 and 3 and 4. So I'm assigning 4 electrons to that carbon. So it's 4 and minus 4 is 0. So these two molecules have the same formal charge. But it turns out that their oxidation states are quite different, right? So let me go ahead and erase all of this so that then we can go and talk about oxidation state. So for oxidation state, what I'm going to do is see if I can select this and move it up here for you and make it, I've got a little bit of a periodic table here, so I want to make it bigger. Nope, that's not working. Okay. All right, so let me share my screen again with you here. I've got that figured out. So I wanted to pull up this portion of the periodic table. So now when we calculate the oxidation state, we assign the electrons differently. So what we're going to do is assign all of the electrons to the more electronegative atom. So if I look at hydrogen here, the electronegativity is 2.1, and for carbon it's 2.5. So carbon is more electronegative than hydrogen. Okay, so I'm going to go ahead and assign all of the electrons to the carbon. Let me move this out of the way. And let's calculate our oxidation state now. There we go. All right, so I'm going to start with the group number, again, like we did for formal charge, and the group number for carbon is 4. And I am going to assign 2, 4, 6, 8 electrons to that carbon. So that's going to be 4 minus 8, which is equal to, equal to minus 4. So the oxidation state for the carbon in methane is going to be minus 4. And if I do the same thing for CO2, I'm going to have a look at the relative electronegativities. So carbon here is 2.5, but oxygen is 3.5. So for any bonds between a carbon and an oxygen, I am going to assign those electrons to the oxygen, right? So let me make this smaller and move this out of the way. So again, I'm going to start with my group number, which is 4. I'm going to subtract the electrons that I assign to the carbon. I'm not assigning any electrons to carbon because I'm assigning those 2 pairs to the oxygen and those 2 pairs to the other oxygen. So it's going to be 4 minus 0 is equal to plus 4. Okay. So here we have methane, which is the most reduced that carbon can be, right? That is at minus 4. And we have CO2, which is the most oxidized that carbon can be, okay? So it's a little different. That's how we calculate our oxidation state. And I want to go ahead and show you just a few more examples, right? So let's move this out of the way, make it smaller, and we'll get rid of that. Okay, so let's take another set of molecules here, and let's see what we can do. All right, so here I have methanol, I have formaldehyde, and I have formic acid. Okay, so for each of these, again, if I calculate the formal charge, I'll let you go ahead and do that. But the formal charge would come out to be 0 for all of these, all right? But my oxidation state is not the same. So here for my methyl alcohol or methanol, again, I'm starting with the group number, which is 4. And which electrons am I going to assign to the carbon? So I'm going to assign 2, 4, and 6. Those last 2 electrons here, right, I'm going to assign to oxygen. So of those 8 electrons in the valence shell of oxygen, I only assign 6, all right? So 4 minus 6 is equal to a minus 2, okay? So that's the oxidation state of the carbon in methanol. Now, if I look at my, my formaldehyde, all right, what electrons am I going to assign to that carbon? I'm going to assign 2 and 4. So my oxidation state is going to be 4 minus 4 is equal to 0. All right. And then for my formic acid, I'm going to go ahead and just assign these 2. All right. So my oxidation state here is going to be 4 minus 2 is equal to 2. Okay. So if we look at these 3, my most reduced among these 3, right, is going to be the methanol. But it's oxidized when compared to the methane, right, the CH4 molecule. Remember, CH4 was at a minus 4, okay? So among these 3, my most oxidized, right, is going to be the formic acid. All right, so I always like to remember Leo the lion says grr. Leo, lose electrons oxidized, and grr, G-E-R, gain electrons reduced. Okay, so the smaller the number, the more reduced, the larger the number, the more oxidized. So again, our formic acid, we have an oxidation state of 2, which compared to the CO2, right, CO2 is reduced compared to the CO2 because the oxidation state for carbon in CO2 was plus 4, okay? So that's just a few more examples, but I think you can see, and we'll show a few more, that when we go from a carbon-oxygen single bond to a carbon-oxygen double bond, right, from here to here, right, this is an oxidation. So generally going from an alcohol to a carbonyl compound is going to be an oxidation. And going from this carbonyl compound to the carboxylic acid is also an oxidation. Okay, ox and ox. And when you go in the opposite direction, that is a reduction. And here to here is a reduction because we're changing the oxidation state of the carbon. Okay, so let's go ahead. I'm going to go ahead and get rid of all of this. All right, and we'll look at some more examples. If I can make this smaller and move this out of the way. All right. Let's see, what do we have here? Let's move this and make it bigger. All right. So here I have an aldehyde, and what you've seen so far are just carbon hydrogen bonds or carbon oxygen bonds. Let's just get rid of that. So here we have some carbon-carbon bonds. Now, when you have a bond between two of the same atoms, you're going to split that bonding pair up because those atoms obviously are equal in electronegativity. So if I'm going to look at this molecule right here, right, which is acetaldehyde, what am I going to assign? I'm going to assign these electrons from the hydrogen, and I'm going to assign one electron from that bonding pair. So now my oxidation state here is going to be 4. I'm starting with the group number. Minus 3 is equal to plus 1. Okay. And now when I'm looking at this molecule over here on the right, this is ethanol. What am I going to assign? I am going to assign these electrons to carbon, these electrons to carbon, and one of these electrons to carbon, right? The electrons from the carbon and oxygen bond are going to get assigned to the oxygen, okay? So what's my oxidation state? It is going to be 4, starting with the group number, minus 2, 4, 5 is equal to minus 1, okay? So I think that you can see now that this reaction going from, whoops, sorry, let me erase that. That is acetaldehyde. Acetaldehyde, an aldehyde to an alcohol. This is ethanol. All right, oops, I forgot the H, ethanol. This reaction is what, an oxidation or a reduction? I'm going from plus 1 to a minus 1. I'm reducing the oxidation state, so this is a reduction, all right? So you're going to be seeing reactions like this. Okay, so I think that's pretty clear. Oh, yeah, there was one thing I also wanted to say. Let me just erase this right here. So I have put in red the atoms that have been added in this reaction. So we've got added an H, right, here, and an H here. Right? So basically what I have done in this reaction is I've added H2, right? H2 across this double bond right here, right? So more broadly, this is a reduction reaction, but more broadly, this can also be considered an addition reaction, right? Because I've added something across that double bond. Okay, so let me go ahead and erase all of this. And we will look at another example. I'll get rid of that. Hello, there we go. All right, I think I did this one. So we'll move that. Let me have this one here. Okay, so What we've seen is increasing the number of bonds to oxygen, and that's kind of a rule that, and one way that will help you to recognize an oxidation reaction, right, is by increasing the number of bonds to oxygen. Yeah, and if you increase the number of bonds to oxygen, that is going to be an oxidation reaction. But there are also other oxidation and reduction reactions that we can see that may not be quite so obvious, right? So when we studied the addition across the double bond of an alkene, we looked at this reaction. This is a catalytic hydrogenation. And so we were adding H2 across this double bond. And again, I have shown the atoms that I've added here in red, okay? We called this an addition reaction, all right? And it is indeed an addition reaction in very broad terms, but the addition, just calling it an addition reaction doesn't tell you anything about how that addition took place. It tells you nothing about the mechanism of that reaction. So you may recall that I also called this reaction a reduction, right? This is a reduction. So how is it a reduction? Let's have a look at the oxidation state of the carbons in the starting material and in the product, right? So again, I'm going to start with my group number for carbon, which is 4. And what electrons am I going to assign? I'm going to assign 2, 4, and 1 from each of the bonding pairs, okay? So I am assigning 2, 4, 5, 6. So this is 4 minus 6 equals a minus 2, right? So that is the oxidation state of each of those carbons in ethene, okay? Let me erase this so I can give myself a little bit more room here. So let's assign electrons in ethane. I'm going to assign 2, 4, 6, and one of those, 7. So I'll just write that down, keep a note of that, 7 electrons. So when I calculate my oxidation state for the carbon, I start with my group number. So it's 4 minus 7. That's equal to a minus 3, okay? So again, I've reduced the oxidation state or the oxidation number for each of those carbons. So that reaction is indeed a reduction reaction. So it doesn't have to just be an increase in the number of bonds to oxygen, okay? And let me get rid of this. And I have one more example that I want to show you. And where did it go? Here we go. Whoops. Hello. Come up here. There we go. Come on. Okay. So we've already seen that going from methane, right, methane to methanol is an oxidation reaction because my oxidation state is -4 for methane, okay? And for methanol, I'm assigning 2, 4, 6. So it is 4 minus 6 or -2, okay? So I'm increasing the oxidation number, so that is indeed an oxidation, okay? But what about methyl fluoride? Let's go back and have a look at our periodic table and consider the relative uh, electronegativities. So here we have carbon at 2.5 and fluorine at 4. So I am going to assign the electrons between the carbon and fluorine bond to the carbon, right? Let me just get rid of this because I don't need it anymore. So if I do that, what electrons from this molecule am I going to assign to carbon? I'm going to assign 2, 4, and 6, okay? So I start again with the group number, so it's 4 minus 6 is equal to a -2, right? So remember that methane was -4. So going from methane to fluoromethane, right, is also an oxidation. So it doesn't have to be just a change in the number of bonds to oxygen, all right? So I hope that this little exercise here has cleared up for you the difference between formal charge and oxidation state. And we'll see some of these reactions when we start talking about oxidations and reductions of carbonyl compounds.